This problem, exercise 4.78, is another challenge problem. And I like this one a lot because we have to think physically about what's going on in order to make progress on this thing. We can't really do it blindly. So let's think about what's happening here. So at the county fair, we have this game, and we launch the ball on a frictionless table, but the table is angled. Okay, so it's not horizontal and it's not vertical. But let's think about what would happen in this problem if the table were horizontal. If the table were horizontal, we'd be basically launching this thing at a certain angle, and the acceleration due to gravity would have no effect on it. It would continue on its constant velocity trajectory. The other limit is when the angle is not 20, but is rather 90. Okay, and in that case, this is basically our standard free fall problem, our projectile motion problem, where we launch the thing at a certain angle, and it's accelerated under the influence of gravity at the usual rate. But in this problem, what we have is we have an acceleration in the plane. So what I'm going to do is I'm going to draw a coordinate system that's in the plane. Y is in the plane. X is in the plane. And so if we think about the y component of the acceleration, well, what we're going to find in this problem is that the acceleration is g, I'm going to say minus g, but it's going to be changed by a factor, that's sine of 20 degrees. Once we recognize that fact, now you can draw a picture if you don't believe me, but that's going to be our acceleration in the y direction. And once we do that, then it basically becomes a free fall problem, projectile motion problem. All right. So let me draw it in now what I've called the xy plane here. Y, x, looks like this trajectory looks something like this. All right. Begin with some initial velocity, it looks like that. Travels a distance, 2.5 meters, before it hits the target. And so the question is, what is the angle theta? That is, this is v0. What is theta? Such that we hit it at just the right spot. So we know the speed. Right? We know the magnitude of v is 3.0 meters per second. Okay. So the first thing that I'm going to do in this problem is I'm going to use something that I've learned and that I hope that you've come to realize. Now, I don't think we've talked about it very explicitly, but in this motion we start with some initial velocity, and through its trajectory the x component doesn't change, but the y component does. And in fact, there's a symmetry to this problem, such that the final velocity in the y direction is minus the initial velocity in the y direction. That is, it has a certain amount of initial velocity upward and a final velocity downward, and they're equal in magnitude but opposite in direction. Now I can use this fact. Right? I can also use the fact that the acceleration in the x direction is 0, which means that I use my standard kinematics guess. X is equal to x0 plus v naught x t plus 1/2 ax t squared. That's 0. I'm going to set that to 0. I'm going to set x and y is equal to 0 initially, which means that my x position is going to be v naught x times time. That's my first expression. My second one is, well, I'm actually going to use this fact along with my other kinematics guess, that the final velocity in the y direction is the initial velocity in the y direction plus ay times t. And then coupled with this fact, I'm going to plug that in, and what I get is I get 2 what am I doing here? Let's see. So time, let's see, 2 v final y is equal to ay times time. Right. And that'll be my other expression. That's going to help us out here. Okay. And so, well, what can I do here? So I can actually use this triangle up here that I've constructed to help me make more progress on this problem. So I'm going to redraw that triangle. Gives me the angle that I'm after. I'm actually looking for this. I know this is V0 y. I know this is V0 in the x direction. Okay. I know this is V0 in magnitude. Okay. So what I can do is, okay, I remember now that V0x is V0 times the cosine of theta, adjacent. V0y is going to be V0 times the sine of theta, opposite. All right. And so what I can do now is I can take my equations from before. We'll take this one in red. And what I'm going to do is I'm going to substitute in V0x. X is equal to V0 cosine theta times time. And then what I'm going to do is I'm going to take this other expression, and what I'm going to do is I'm going to substitute it in. I'm going to substitute in my expression for V0y. Except I know that this is actually minus V final y. And so what I can do here is I can actually plug this in. So 2 times minus V0 sine of theta is equal to ay times t. Ay is minus g sine of 20 times time. Okay. All right. And so this is kind of interesting here. So what I'm going to do is I'm going to keep the same expressions, but I'm just going to move them around a little bit so that they look a little nicer. Okay. So x is equal to V0 cosine theta times time. And over here, I've got the minuses cancel. 2 V0 sine of theta is equal to g sine of 20 times time. So this is times and this is times. And so if I take these two expressions and if I divide them, so I get x over 2 V0 sine of theta is equal to, t's cancel, V0 cosine theta divided by g sine of 20. The sine of 20 is just a number. All right. Okay. And so here's what I can do. I'm going to rearrange this. I'm going to bring this to the other side and that to that other side. And I get x times g sine of 20 is equal to v squared, v0 squared, times 2 sine of theta cosine theta. Okay? But this actually turns out to be, by an identity, sine of 2 theta. I'm going to bring that to the other side. And so what I get is I get x g sine 20 divided by v0 squared is equal to sine of 2 theta. I take the arcsine of both sides, and I can get that. I get arcsine of x g sine of 20 divided by v0 squared times 1/2 is equal to theta. And so that's my expression. And when I plug in all the numbers, I know x from before, x is 2.5 meters. I know g, it's 9.8. I know 20 degrees, sine of 20. And then I know v0. It's 3 meters per second. When I do all that and I plug it in, I get 34.3 degrees.